Remember, I always talk about using our unit circle to kind of help us guide through the process. So let me open up our unit circle over here. So since this is cotangent of x equals 3, remember cotangent is the reciprocal function for tangent. Or you can think of this as, we define tangent of x as sine of x over cosine of x. So you can think of cotangent of x, as the reciprocal. So that's cosine of x over sine of x. So we're basically looking in our unit circle where when you divide cosine value by the sine value, your answer comes out to be square root of 3. So, of course, the first thing you are doing is going to all the ordered pairs where you see square root of 3 as part of the cosine or the sine function. So of course, that's going to be this guy over here, this one over here, this guy. So I think basically everything that is divided by 6 or divided by 3 in your theta values. But, obviously it's not going to be all of them since we are talking about cotangent as cosine of x over sine of x. We have to see which one of these will end up giving us square root of 3. So if I take my first set of ordered pairs here from pi over 6, you can see this is square root of 3 for the cosine function, square root of 3 divided by 2, and the sine function is 1/2. So if I use those two values, square root of 3 divided by 2, which is cosine, divided by 1/2, which is sine. Remember, we keep the first fraction the same, invert the second fraction, and that changes division to multiplication. And then here, of course, our 2's cancel out, leaving us behind with square root of 3. So this was actually coming from the angle pi over 6. So pi over 6 is going to work because that gives us the square root of 3. Now, if you try to do the same calculation with this angle over here, pi over 3, it's actually not going to work out because we are going to be taking 1/2 and dividing it by square root of 3 over 2 for the sine function. So that would actually give you 1/2. Then division changes to multiplication. Invert your second fraction, and that becomes 2 over square root of 3. So, of course, 2's cancel out, leaving us behind with 1 divided by square root of 3. And when you rationalize your denominator, you will actually have square root of 3 over 3, which is not what they are asking us to find. So this guy does not work out for our example over here. So these guys are gone, which means this guy is not going to work out. Wherever you have your square root of 3 on the sine value is not going to work out. So, automatically takes these 4 out of the equation. Now, can we use 5 pi over 6? Can we use 7 pi over 6? Sorry, I did the wrong one. I cannot use this. This guy should be okay. And can I use 11 pi over 6? Which one of these will satisfy to give me cotangent of x equals square root of 3 only? So out of those 3 remaining angles, 7 pi over 6, Abdul Aziz, which is this guy. Yeah, and the reason this will work is because both my numbers are negative over here. So since both of them are negative, when I do my division, negative divided by negative will become positive. So this angle will actually work, 7 pi over 6. So yeah, very nice, Shu and Abdul Aziz. But 5 pi over 6 is not going to work because my cosine is negative, but sine is positive, which means my negative sign will stay. And I do not have, negative on my function value over here. So I don't want to have negative, which means this angle is out. And same thing over here with 11 pi over 6. You've got negative 1/2, but that's a positive. square root of 3 over 2. So again, that means when we do our division, the negative sign will stay. So this guy is out. So only two angles. And you know, this is going from 0 to 2 pi. So that's going to be your pi over 6 and 7 pi over 6. So remember, this is going from 0 to 2 pi. Now we have to go from 0 to negative 2 pi because that's your interval from positive to negative 2 pi, or rather negative to positive 2 pi. So that means we now need to go in the clockwise direction and figure out what these two angles on the negative side are going to be. So what does negative pi over 6 look like in the clockwise direction as a negative angle? And same thing with 7 pi over 6. What does that look like as a negative angle? So what are the negative counterparts for pi over 6 and 7 pi over 6? Okay, let's see. I've got Katie and Abdulaziz negative 5 pi over 6, negative 11 pi over 6. Okay, let's take a look here. So yeah, they are going to be negative counterparts. So, you know, your pi over 6 is going to be the negative counterpart for this angle. So this guy will become negative 11 pi over 6. So that looks good. And then your 7 pi over 6 is the negative counterpart for this angle over here. So that will become negative 5 pi over 6. So yeah, very nice. Very good. And those would be our two negative angles. So let's see, we will add to this list negative 11 pi over 6, negative 5 pi over 6. So these are the four angles that you are looking for in this interval, going from negative 2 pi to positive 2 pi. And you can verify those answers by looking at number 19 over here. Okay. So that's kind of how you want to break down these problems where they ask you to find the solutions for the given interval. So Scotty, does that kind of help you out? Yeah, that makes sense. Okay, very nice. Very good. Did anybody else have any other question on this example or just on anything else you're working on right now? Okay. Ozzy, you really need to turn your video on there, buddy.
I turned mine on earlier and you turned it off right away, so I couldn't.
Okay. So this is where we had kind of left off last time. We were looking at, you know, how these compositions work out. I think we had looked at, you know, one of our initial examples. So let's continue with this discussion of, you know, what happens when you are working with compositions, because remember I was telling you that you really have to look at what the domain and range for your function values are going to be before you can decide if you can find a solution to these or not. So let's take a look at what we had as our next example, number 27. So let's go into our textbook here. So we were in section 1.7. All right, here we go. Actually, this is a calculator problem, so I'm going to skip that. Let's go to 32. Oh, I didn't realize I had picked that many calculator examples. Okay, let's jump to 46 over here. Okay, so this is where they're asking us to find the exact value for our expression. So let's take a look at this guy. We are doing number 46. Whoa. Okay, so as you can see, this is a composition between tangent and arctangent of 45. Okay, so let's go back and take a look at those domain and range values for the tangent and arctangent function. So we're basically saying x should be a real number and y should be between negative pi halves and positive pi halves. So if you look at the example we have over here, you've got tangent on the outside and arctangent on the inside. So that is, of course, going to make a difference at, are you looking at the x values or the y values? So if you look at this guy over here, you've got tangent on the outside, arctangent on the inside. So this x value has to be any real number. And if it is a real number, you get the answer of x. So, of course, 45 is a real number. So since 45 is a real number, you actually don't have restrictions on this because this guy says if x is any real number, then you can actually get that same value as your answer. So tangent of arctangent of 45 will actually come out to be 45. And since we say this is a real number, this can be a positive number, negative number. It can be zero. Technically, it can be, fraction, something with pi in there, any of those, as long as it's a real number, it will satisfy this requirement. So, this guy, no restrictions, and you get 45 as your answer. But, of course, if it falls outside of your domain and range, then you got to be careful about, what kind of answer you come up with. So this was a real straightforward answer. Just look at the format of the composition and then see if you're falling in that domain or range or not. But what happens if it does not fall into a domain and range? So let's take a look at an example like that. So 49. So here you've got arc sine on the outside and then sine of 9 pi over 4. So again, let's take a look at what this format does. So we're looking at arc sine of y. So in this case, your y value has to be between negative pi halves and positive pi halves. And you will see how we are including the endpoint. So as long as this y value is going to be between negative and positive pi halves, including those numbers, then your answer, will be the same y value. If it falls outside of this range, then, of course, you will have no solution. So you kind of have to look at this 9 pi over 4, and you have to think, is 9 pi over 4 between negative and positive pi halves? And if it helps, look at the unit circle again to help you visualize it. Okay, so I'm actually going to try and figure some of this mess out. So you're looking for 9 pi over 4 and trying to see, is 9 pi over 4 between positive and negative pi halves? So how are you going to do that? Where is our 9 pi over 4 going to fall into? The first quarter, Abdul Aziz. Okay. So, you've got basically 1 pi over 4. This guy will be technically 2 pi over 4 because that simplifies into pi halves. This guy is 3 pi over 4. This guy would be 4 pi over 4. This is, of course, 5 pi over 4. This guy would be 6 pi over 4. 7 pi over 4. This would be 8 pi over 4, which we know simplifies to 2 pi. So yeah, your 1 pi over 4 is actually equivalent to 9 pi over 4. Basically you are coming a full circle and then coming back up that pi over 4. All right, so now that we know where 9 pi over 4 falls, is it between negative pi halves and positive pi halves? Because that's the restriction on your y value for arcsine of sine. So is 9 pi over 4 in that range of negative pi halves to positive pi halves? Abdul Aziz, you're saying no? Where is your negative pi halves on this circle? We know where positive pi halves is. Where's negative pi halves? Very nice. Yeah, Billy and Abdul Aziz. When you go in the clockwise direction, this guy becomes negative pi halves. So you are actually looking at the first and the fourth quarter of your unit circle. So you're actually looking at this first quarter. So now I ask you that question again. Is 9 pi over 4 between negative pi halves and positive pi halves? Yes, it is. Yeah, because right here you can see where your 9 pi over 4 was equivalent to pi over 4. So those are the kind of techniques you are using to help yourself out with these types of examples over here. So again, we were looking at number 49. And in this case, since negative pi, 9 pi over 4 falls in that range of, negative to positive pi halves, you will actually have 9 pi over 4 as your answer for number 49. If it did not fall, then, you would go with impossible, I think. So since we have to stay within our values, you actually do need to simplify this. So you're kind of removing that 2 pi from it. Remember when we had talked about coterminal angles? So you will actually rewrite this guy as the pi over 4. And we're basically doing this so that we can stay in the range of negative pi to pi over 4, because technically 9 pi, you are 9 pi over 4, you're having to make a full circle. So to kind of stay within that range, we will rewrite this as just pi over 4. And we know these are equivalent angles, so we're not really changing the answer. We're just getting rid of that 2 pi, that full circle from this. So you can just see how, you kind of have to visualize this either using the unit circle, or, you can try and do this by using coterminal angles and that kind of thing. But I actually just prefer the unit circle because I like to be able to visualize this. Okay, so just 2 different examples using the tangent and the sine function. Now let's see. I also had number 53, which is kind of similar in concept to the other example, but here instead of doing, the original function and the inverse, because, in both these examples, tangent and arctangent were inverse functions of each other, sine and arcsine are inverse functions of each other. But now look at number 53, because you are now using cosine with arctangent, right? And they are not inverse functions of each other. So let's take a look at, how we go about solving something like this. So the first thing you have to do is, again, we are still restricted by the domain and range. So you have to look at, again, for the cosine function and the arctangent function, what your domain and range values are going to be. So for the arctangent, again, your tangent function, arctangent, the domain has to be between x for all real numbers and the y value, negative pi halves to positive pi halves. And then for the cosine function, your domain and range values go from -1 to +1 and 0 to pi, including the y values. So those are the kind of things we got to keep in mind. Start with the inside function. What will tangent inverse or arctangent of 2 look like? Is that going to be within the defined range of your functions? So arctangent or tangent inverse, as they're calling you, of 2. So that's this guy over here, arctangent of 2. Is that going to be within our defined domain for the function? The value of 2? Yes, no, maybe. Yes, it is. Because when we're saying arctangent of the x value, and this value is 2, well, of course, that is a real number, because 2 is between negative infinity and positive infinity. There should be actually no equal to there. So yeah, it is going to be within the real number for our inverse tangent functions. If that is defined, then we can move on to our cosine function. So let's take a look at this. I'm actually going to write this guy out over here. Okay, so this guy is number 53. We have cosine, tangent inverse of 2. Make sure I have the right problem here. Okay, so let's take a look at this guy. Now, when it comes to solving examples like this, it's going to be a little bit different than what you just saw with the previous 2 examples. So what we will need to do here is actually use, again, a little bit of visualization. So let's do a little grid over here. Now, starting with our central angle. Let's create here. So now when we're talking about tangent inverse of 2, remember how we had mentioned that you can think of this as equal to, I guess we'll do a y value. So if I wanted to rewrite this, I can take and write kind of like tangent on both sides of my functions. I can take a tangent on both sides, and that will end up giving us 2 equals tangent of y. So we actually want to apply that, because tangent function is actually what's going to help us kind of associate with the cosine function. So we're taking this expression of tangent inverse of 2, set it equal to whatever variable you want to. We're just going with, since 2 is the x value, we're calling this equal to y. And then when you take a tangent on both sides, essentially on the left-hand side, you can think of the tangent and tangent inverse kind of canceling each other out, nullifying each other. So you're left with 2 on the left-hand side and then just tangent of y on the right-hand side. So this tangent of y is obviously the angle value. So if this is 2, I can write this as a fraction as 2 over 1. We define our tangent function as opposite over adjacent. So from this angle, the opposite would be 2 and the adjacent would be 1. And then we talk about the cosine function. Well, for the cosine function, cosine of theta we define as adjacent over hypotenuse. So we know the adjacent side is 1. We just have to find what this hypotenuse side is. So, you can use, well, let me ask you this. What method would you use to find the hypotenuse for our triangle over here? What method can you use? We know the opposite side. We know the adjacent side. Yeah, I think the most straightforward, very nice, hero, would be the Pythagorean. Yeah, Alicia, very nice. So let's use the Pythagorean theorem to help us out here. So remember, Pythagorean is a square plus b square equals c square. So you can think of your a square value as 2 squared, b square as 1 squared. And then for our hypotenuse, we have to find the c square. So what do you think your hypotenuse value will come out to be? And don't convert it to a decimal answer if you don't get an integer answer. So let me see what you come up with for your hypotenuse using the Pythagorean theorem. All righty, bunch of answers coming through. Let's see, I've got Abdulaziz, Hero, Alicia, Shu, and Katie. All of you have square root of 5, square root of 5, Billy, Jack. Okay, very nice. So square root of 5, yeah, because you are doing 2 squared, which is 4, plus 1 squared, which is, of course, 1. So 4 plus 1 gives you 5. And then to get, c by itself, we would take a square root. Technically, you would have a plus or minus, but, of course, we're not really looking at the minus answer. So you will just keep it as square root of 5 for your c value, the hypotenuse. So there you go. This guy will be square root of 5. Alrighty, so now go ahead and rationalize this, and what will you end up with? 1 over square root of 5 using this idea of adjacent over hypotenuse. So rationalizing that will end up giving us, yeah, very nice, square root of 5 over 5, because we would multiply both our numerator and denominator by square root of 5. And at this point, I would imagine you guys know WebAssign kind of keeps going back and forth between how they want you to type your answer. So it can be this guy, or it can be this guy. So just as a quick review, the first thing we did was make sure that tangent inverse of 2 even exists. So we made sure, that 2 was going to be part of the domain of the tangent inverse function. And we know since your domain is all real numbers, this value of 2 is okay. So then we just used the conversion of converting it from a tangent inverse to a tangent function. We got tangent of y equals 2. We can write this as 2 over 1 so that we get our opposite over adjacent. And then we're just putting it in our little right triangle over here to help us come up with the cosine function. So once we have the opposite and the adjacent sides, then using our Pythagorean theorem, we can come up with the hypotenuse, which came out to be square root of 5. And then using that, we're basically defining our cosine of theta, which came out to be 1 over square root of 5, or as a rationalized answer, square root of 5 over 5. And since this guy was an odd number problem, you can actually check that solution here in your example. So that's kind of how these, where you're using two different functions, you're going to have to solve these examples. So let's take a look at our next example here. Number 66. This one is getting a little bit more generic because now instead of giving you a number, we have 3x as the value inside our parentheses. So let's take a look at this guy. So they are asking us to write an algebraic expression. Let me bring this guy down. So they're saying write an algebraic expression that is equivalent to the given expression that we have here. So this time you will see we have secant of arctangent of 3x. So how do we come up with the algebraic expression for our secant function over here? So let's go ahead, write this guy down. So secant arctangent of 3x. So since this is given to us in a more generic form, right, you're only given 3x. So we're going to assume that that x is going to be part of our domain, between negative infinity to positive infinity, because this is again an arctangent function. So we're just going to assume that because, since we don't know what x stands for, we are not really able to verify it. So like I showed you before, take the inside part. So that's the arctangent of 3x, and we'll set it equal to y. Then, again, take your tangent on both sides. So on the left-hand side, the arctangent and tangent nullify each other, and you're left with 3x equals tangent of y. So very similar to what we just did with number 53, keeping that same thing. And again, you can think of this as 3x over 1 to kind of get that opposite over adjacent thing going. And then we'll create our little triangle again. If this is your theta, then the opposite side would be 3x. The adjacent side would be 1. So that, of course, tells us then we've got to find our missing side. So you will see again, even though we're dealing with this in generic 3x terms, we're still going to be following the same rule. So again, we need to use our Pythagorean theorem over here. And what do you think that hypotenuse will come out to be?
What the fuck?
Sorry, would you say that again? Okay, so I see something in chat over here. Abdul Aziz, you've got 9x squared plus 1. Chu, you had square root of 10. Okay, so let's take a look at this. Since we are trying to find the hypotenuse, again, this will be 3x squared plus 1 squared. And then, of course, if we call this guy c squared again. So 3x squared, when you multiply 3x times 3x, will give you 9x squared. 1 squared is just 1. To get c by itself, of course, you would end up taking a square root on both sides. Plus or minus, there we go, square root of 9x squared plus 1. So it looks like, Shu, you're just adding the 9 plus 1 to make it 10, but we can't do that over here. Jack, yeah, very nice, 9x squared plus 1 inside the square root. And then, of course, you're just discarding the negative sign. So our hypotenuse over here is going to be square root of 9x squared plus 1. Okay, so now that we have all three sides of our triangle over here, how will you use that to find your secant function? So how will you come up with the secant function? Think about how you define secant. Abdulaziz, yeah, because remember, secant is the reciprocal function for your cosine. So secant, you know what, let's use theta. Secant of theta is basically 1 over cosine of theta. Or you can think of this as, if we define cosine of theta as adjacent over hypotenuse, then we define secant of theta as Abdulaziz has in chat, hypotenuse over adjacent. So that's what you will use to come up with your secant function using that ratio over here. So let me see, did you guys have an answer in the chat for what this finally ends up looking like? I don't think I saw the final answer, did I? No, so go ahead and send me what you think your final answer should be based on this idea of hypotenuse over adjacent. Oh, it shouldn't take you that long. Yeah, because when you talk about hypotenuse, our hypotenuse value is square root of 9x squared plus 1. Your adjacent to the theta angle is 1. So, basically you're dividing that by 1, which ends up giving you square root of 9x squared plus 1. So yeah, very nice, Katie. So that's going to be your answer. So again, guys, you are starting out with that inside function first. So again, since this was tangent inverse of 3x, we're just assuming that x is going to be within the domain of our inverse function for tangent. So we can go ahead and take our arctangent of 3x, set it equal to y, take a tan on both sides so that we're able to convert this into 3x equals tangent of y. I'm rewriting that 3x as a fraction, so 3x over 1, so that I can create that opposite over adjacent thing going. Put that in our right triangle, opposite and adjacent sides. Then using your Pythagorean theorem, you were able to calculate the missing side, which was the hypotenuse in this case. Since the secant function is the reciprocal for the cosine function, if cosine is defined as adjacent over hypotenuse, then secant is defined as hypotenuse over adjacent. So that means you're taking the hypotenuse side, dividing it by the adjacent side, which gives us this fraction of square root of 9x squared plus 1, whole thing divided by 1, of course, it just gives you the square root of 9x squared plus 1. And those will be same kind of steps, you would try and employ with these different types of examples. But however, if you're working on this part of the homework, where they're actually giving you numbers, then make sure you verify that those numbers are going to fall into the domain or range of your inverse functions before you start solving them. So anyone have question on this example 66 over here? Okay. And then I had one more example for us to look at, which is this, I believe it should be an application number 102. Let's take a look at that guy. Okay, so we will actually need this image from the previous example, but of course our numbers will be slightly different. So we're looking at number 102 over here. This one is talking about granular angle of repose. So basically they're saying when shelled corn is stored in a cone-shaped pile 20 feet high, the diameter of the pile is about 94. So you can kind of imagine, our shelled corn being in this conical shape, kind of like you're seeing in this illustration on the top. They're telling us this pile is 20 feet high. So, for our example, that would be 20 feet. And then they're telling us the diameter of the pile. So that's the diameter is about 94 feet. So they're saying, draw a diagram that gives us a visual representation of the problem. So, we're instead of drawing, we're just using this guy from the previous example. Label the known quantities. We've taken care of those. Now they're asking us to find the angle of repose, and you can see where they have marked that angle in example 101. So that's the angle we are trying to find for the shelled corn. So what do you think you can do to find that angle? What will we need to, what function or what process will you need to use? The arctangent function, Abdul Aziz. Okay, so how will you set up your equation? The height of the pile with division by the radius. Okay, let's take a look at this. So let's move this example to our I'm actually going to keep this while we write these numbers down. So this is number 102. All right, so I'm actually just trying to get the idea of the triangle over here. We know this is 20 feet and we know the entire diameter is 94 feet. So the first thing we do want to do is, find the radius. So, obviously the radius would be half of the diameter. So that would be your 47 feet, right? Because 80, yeah, 47 feet for the radius. Now, if we are thinking about this as the angle of repose, then if you think about the tangent function, you have the opposite and the adjacent sides, right? So we can rewrite this guy as tangent of theta equals opposite over adjacent, which would be opposite is 20 feet, adjacent is 47 feet. But since we are actually interested in the angle, that's where the arctangent or the tangent inverse function will come into play, right? That Abdulaziz was talking about in chat. So kind of like we were doing in the previous examples, once you have this tangent theta equals 20 over 47, then we can use this idea of tangent inverse on both sides of our equation over here. So, you know, again, these guys would kind of nullify each other, just leaving us behind with theta, and you would have theta equals tangent inverse. And let's see if they want us to leave it as an exact answer. We don't really have instructions if they want a decimal answer or not, but let's put it in a decimal form. So what do you think your angle of repose will come out to be for this example here? And we'll just round it to 2 decimal places. If your homework says more, then you can do more decimal places in homework. And remember, this is where you are using that tangent inverse function on top of the tangent key in your calculator. Just make sure you are in the right mode. Did they tell us? They're not really telling us, but you know what? Let's do this in degree mode. So just make sure your calculator is in the degree mode, and then we are doing tangent inverse. And I can see some of you have already calculated that. So very nice. 23.0513. It keeps going, but we'll just do 2 decimal places. And, you know, again, use your homework instructions to see, do they want radian? Do they want degrees? You know, how they're asking you to round your answer. But right now we're doing this in degrees. So that is going to be your angle of repose. So this was part B of our problem. And then part C, they're actually changing the value on us. So for part C, they are saying, how tall is a pile of shelled corn that has a base diameter of 60 feet? So they're actually keeping the height of the pile the same at 20 feet, but instead of having 94 feet as the diameter, they want to know what happens with 60 feet. So basically you are changing, and again, I'm just going to do the triangle part of our image over here. This is still theta. We're still keeping this at 20 feet, but now they are changing the diameter at 60 feet. So I'll give you guys a couple minutes here to finish your calculation, and let me see what you come up with for your angle of repose when you change the diameter from 94 to 60. And so how will you need to change this formula and come up with your answer? So those of you who have an answer, can you tell me what part of the equation you changed?
47,
What did that change to? Very good.
30.
Yeah, because your radius is changing, right? When they're telling you that the diameter of your pile is going down to 60 feet, then that of course tells you that the radius of your pile has obviously also transformed. So in this equation where you had tangent of theta equals 20 over 47, that actually changes to 20 over 30. So yeah, when you do the arctangent function, you're looking at theta equals tangent inverse of 20 over 30. So it's just one simple change. So what do you notice when the radius becomes smaller? What happens to your angle of repose?
Larger.
Very nice. The angle becomes larger. So let's see, you guys had 33 point something.
6'9".
33.9. Yeah, very nice. And I've got Scotty, Katie, Shu, Billy. Yeah, great job, guys. Very nice. And again, remember, we're leaving this in degrees for now, because I think that's what they did in the previous example. So the idea is the smaller your radius is going to become. So, if you make your radius smaller, the angle is going to get larger. So that angle becomes larger when the radius is smaller, is basically what we're noticing. So just an example to kind of show you how these inverse functions can be used in applications. So did anybody have a question on this example over here? Okay, so that was the last part of section 1.7 that we wanted to talk about. And again, guys, if you have not seen the video lecture, I obviously strongly recommend you guys to go look at that. There's a bunch of different examples with different values to just kind of get you comfortable working with these different calculations over here. The last section in this, chapter 1 we want to talk about is section 1.8. So this is where, we're kind of falling back into a little bit of our right triangle trigonometry, kind of helping us solve these triangles. So that's going to be the first part over here. If you look at this first example, any triangle, right triangle or otherwise, it will have 3 sides, 3 angles. So for, the right triangle, if you know one of those 2 acute angles, since we know this angle over here is always going to be 90 degrees, if you know one angle, you can always calculate the second one, because we know the remaining 2 angles are also going to add up to 90 degrees. So you can just take 90 degrees minus this angle of 34.2, and that will give you the missing angle. And then using our trig functions, we can come up with the missing sides because, obviously they are giving you one of the sides. So we should be able to find the missing sides by using the angle measurement and, the given side. So let's take a look at an example that I have for us over here. Number 6. Okay, so this guy over here, they're basically asking us to solve the right triangle by finding all the unknown sides and angles, and they're telling us to round our answers to 2 decimal places in this. So let's start with number 6 over here. So you can see angle B. Remember, we use capital letters for angles and small letters for side. So they're telling us angle B is 25 degrees and side B is 4. So now you need to find angle A. So what do you think the measurement for angle A is going to be? Okay, Scotty, Abdulaziz, very nice. Yeah, so remember, either you can do all 3 angles add up to 180 degrees, if that helps you out. But, since, like I said, we know this corner here is a 90-degree angle, so there's really no reason to include that guy. So the remaining 2 angles, A plus B, we know add up to 90 degrees. So if you know angle B, to find angle A, you can just do 90 degrees minus 25, which, as you guys told me, comes out to be 65 degrees. So that guy's taken care of. Now we need to find the missing sides A and C. So let's see, which one do you want to find? Side C, side A? Does it really matter? Because depending on which side you want to find, you will have to decide which function you want to use. Okay, so Abdul Aziz is saying side C. So let's talk about side C next. Okay, so this guy is done. I'm going to put him under. All right, we're finding side C. So with side C, my recommendation would be, of course, we want to use this known side of side 4, measurement 4. So you want to probably use angle A over here, which is our 65-degree angle. And so which function would you use if this angle A is the angle you are using? We have side B and we are trying to find side C out of basically our 3 main functions, sine, cosine, and tangent. Which function would you go with? And Abdul Aziz, why are you using cosine? Yeah, because if you look with respect to angle A, side B is our adjacent side, side C is the hypotenuse. So adjacent and hypotenuse come from the cosine function. So you will be using cosine of A, which is angle A, adjacent over hypotenuse. So you are basically doing cosine of 65 degrees equals adjacent, which is side 4. Hypotenuse is side C. So how are we going to calculate that? What will you have for this? So while you guys are calculating this, I'm actually going to transfer this over here so it doesn't look like a mess. This is kind of what we have. So do you have an answer for side C? Nobody has an answer yet? Okay, Abdul Aziz, Billy, you guys came up with 9.46. Jack, you're at 9.5. So yeah, they're actually asking us to round this to 4 decimal places. So you can actually leave it as 9.46. So this is kind of where I had left you guys off. So if you want to find side C, you will basically multiply both sides by side C and then divide the left-hand side by cosine of 65 degrees so that we can get side C on one side, everything else on the other side. So that will end up giving you side C equals 4 divided by cosine of 65 degrees. So just make sure, guys, your calculator is in the degree mode, and it should be because that's where you were for the last example. So as long as you haven't changed that, you should be good to go. And so your raw answer is coming out to be 9.4648. So when you round it to 2 decimal places, it's going to be 9.46. So we have found side C now. So that leaves us with just side A, because we have obviously all 3 of our angles. We have 2 of our sides. So here's my recommendation when you're working on these examples. Do not use side C to help you find side A. And the reason for that is side C is a number we just calculated, and that's a rounded answer, right? It's not an exact answer since we rounded it to 9.46. So if you use side C to help you find side A, then it's actually going to be further rounded down, and it will be a little bit off in accuracy. So go back and find the known numbers that you had. So, angle B, side B, angle A, because those are not rounded numbers. Eusebio, let me email you because I'll need to check my schedule for Wednesday. I'm not sure, but I'll check my schedule and email you, okay? So to find side A, guys, which function would you use so that you're avoiding using the side C? What would you do for side A? Tangent, Jack and Katie. Alrighty, so let's go back to side A over here. So if you use angle B, for that, you can get the opposite side as, side B, and the adjacent side would be side A. So yeah, very nice. We can actually do tangent on angle B, which would be opposite over adjacent. So the opposite side would be side B, adjacent side would be side A. So that would be tangent on the 25-degree angle. And that would again be 4 over A. And then same thing, multiply both sides by A, divide by tangent. And so let's see what values you are coming up with for side A. So I'm actually going to show you here what we're talking about while you calculate that. Okay, looks like you guys have your answer. 2 decimal places. So I've got 8.58, 8.5780. Katie's, Jack, and then Scotty and Billy, you guys had 8.58. So yeah, again, rounding it to 2 decimal places, very nice. So multiply both sides by A, divide by tangent of 25 degrees. Basically, you're switching the places between A and the tangent function, essentially.
Why did we use 25 degrees instead of 90?
Because when you are talking about, well, you could have actually done it with the angle A also, now that I think about it, because then this guy would be opposite and this guy would be adjacent. So yeah, technically, you can do the tangent function on angle A. So opposite and adjacent would be A over B. It should still give you the same answer because this would be with the 65 degree. A is missing. B is 4. Yeah, it will be the same. Yeah, Abdulaziz. So in this case, yeah, this is actually one step smaller because you just multiply both sides by 4. Get A by itself. So yeah, Jack, thank you for asking that. I wasn't really even thinking in terms of angle A. I just went directly to angle B. So this would be tangent of 65 degrees multiplied by 4, and you should get the same answer no matter what from both of those angles. So let's do a quick check. I will do 4 divided by tangent of 25, which is giving me 8.5780. So round it off 2 decimal places. That's 8.58. And if we did 4 times tangent of 65 degrees, same thing, 8.5780, which rounds off to 8.58. And that's the greatest thing about working with these kind of examples, because you can see no matter which angle you went with, you still got the same value for your side A. So you can use angle B, you can use angle A and still get the same result. And you could have gotten the same thing if you had used angle B to find your side C also. It would have worked out and given you the same example. Jack, does that kind of help you that either way it works out? Yeah. Anybody else have a question on this example here, guys? So, and again, if you go through and look at your video lecture for this section, you will again see, we use kind of different angles and measurements just to kind of show you. But then we're getting into actually applications of how you can use this idea of solving a triangle into actually applying this to, real world situations. So we'll pick that up next time because, obviously we're not going to have enough time to look at an application, but that's kind of where we're headed. So my goal for Wednesday's class is to finish section 1.8, since we are taking our exam for 1.5 through 1.8 next Monday, a week from today. So we want to try and finish the applications. I've picked up a couple different applications to show you, and then we actually also get into this idea of bearing. So if you guys have ever been on a sailboat or something like that, you will see bearing, and that kind of thing is always taken into consideration of where you're headed on the water. So we'll be talking a little bit about that as an application also with this. So please keep working on your homework. All the homework and quizzes are open for you. You get stuck on anything, and Scotty, I saw that you sent me a couple more questions. I will look at them during my break and get back to you. But yeah, if any of you have questions on homework, please let me know. So be careful, everybody. Take care, and I will see you on Wednesday morning. So stay safe, guys. Be careful. See ya. Bye, everyone. Take care.
Hey, I had a quick question if I could.
Yeah, sure.
I have some other problems I need to work out, but I'll try to do